Distant School. Cosmic Meteotectonics. Lecture number 1 describes electrical network model galaxy helioplanets background. Here we continue. There were 186 pulses of high-energy particles with energy more than 10 mega-electron volt, taken by solar isotope spectrometer in the long-term 2004 to 2014 interval. Dates are shown in Table 0201, where the number is the sequence number, year, month, day. The hour, universal time, the sign minus sign of particle rate change, plus increasing, minus decreasing. A minus and a plus meaning first decreasing, then increasing. N, particle rate change in time of PeP, energy more than 10 mega-electron volt. By a factor of n, large N, number of measurements in time of PeP, energy more than 10 mega-electron volt. Tau, pulse ratio of adjacent pulses. Table 0201 shows that pulses of high-energy particles, energy with more than 10 mega-electron volt, occurred in the Earth's magnetosphere with an average pulse ratio about 17.9 days or about 0.65 helioday over a long-term interval, from the 1st of October 2004 to the 31st of March 2014. 31 pulses of high-energy particles with energy more than 10 mega-electron volt were bipolar. Figure 0201 shows monthly Wolf numbers over a long-term interval, the 1st of October 2004 to the 31st of March 2014, and pulses of high-energy particles with energy more than 10 mega-electron volt over the same long-term interval. It is obvious there is no connection between both phenomena. Conclusions can be drawn through comparison of data from web pages and geophysical, cosmophysical, and heliophysical data. Contrastively, pulses of high-energy particles with energy of more than 10 mega-electron volt observed close to Earth did not connect with any stationary processes observed in the subpart layers of the Sun and Earth. This implies, in the framework of cosmic meteotectonics, that these pulses are the results of connections between Earth's cavity and cosmic wires. Such cosmic wires carry current inside the solar system because of its interaction with the galaxy cavity. These connections were quite short events, lasting usually no more than these hours. They did not occur every day, and were completely dependent on the state and orientation of galaxy heliocosmic geoelectrical network structures. To support conclusions, it should be noted that pulse of high-energy particles with energy more than 10 mega-electron volt, number 49, began from particle rate around 3 protons per square centimeter, and at the same time there was particle rate about 400 protons per square centimeter in the pulse of high-energy particles with energy more than 10 mega-electron volt burst. Bipolar pulse of high-energy particles with energy more than 10 mega-electron volt, number 136, shows similar behavior. The pulse number 136 began from 0.3, while several days high-energy particles with energy more than 10 mega-electron volts anomaly had particle rate about 8. This implies, in the framework of cosmic meteotectonics, that pulses of high-energy particles with energy more than 10 mega-electron volt, number 49, and number 136, had also occurred in the galaxy heliocosmic geoelectrical network structure and the prolonged anomaly of pulses of high-energy particles with energy more than 10 mega-electron volt, shown in Figure 0202 and 0203, had occurred in the heliocosmic geoelectrical network structure. Thermal crisis in geophysics is not the least factor for a deep understanding of how does Earth's interior work. Since the first quarter of the 20th century, investigators have been carrying out the scrupulous calculations of the heat produced by radioactive isotopes decaying deep underground. The results have allowed the conclusion that the reality differs from the obtained results. This is the so-called thermal crisis. Close scrutiny of Clark's, in other words, the percentage of units of isotope mass per unit rock mass, and then calculation of radiogenic heat flux, has caused a sensation among investigators of Earth's interior heat energetics. Recently, an international team of physicists used the CAM-LAND detector in Japan and the Borexino detector at Laboratori Nazionali del Gran Sasso in Italy to measure the flux of antineutrinos emanating from deep within the Earth. According to theory, the radiogenic deficit of the heat flux deep within the Earth is very high. The amount of heat flux obtained by detectors is more than predicted by the model, but much less than a total flux of 47 plus or minus 2 terawatt. Only about 50% of the heat given off by the Earth is generated by the decay of radioactive isotopes. CAM-LAND collaborator Stuart Friedman of the Lawrence Berkeley Laboratory in California says, "One thing we can say with near certainty is that radioactive decay alone is not enough to account for Earth's heat energy." He continues, "Whether the rest is primordial heat or comes from another source is an unanswered question." Thus, the theoretical model of heat flow within the Earth does not represent the reality, and a better model of its source must be developed. The question goes on to ask, what is the alternative source of the Earth's interior heat energetics? Moreover, the question is of crucial importance for the development of the earthquake foci model that can only be done after the alternative model of heat flux source in the Earth's depth has been investigated. Therefore, the assumption was grounded in the frame of the many-particle theory, non-local statistical mechanics, developed by Anatoly Vlasov, who published his main investigations between 1938 and 1978. From the perspective of Vlasov's theory, vortex models of deuterons migration, enrichment and fusion in mesoscopic cluster around 10 nanometer in diameter units of the Earth's interior were defined, formed, and investigated. A deuteron is the atomic nucleus of a deuterium atom, or deuterium ion D+ or 2H nucleus. This is a nucleus of an isotope of hydrogen, half heavyweight hydrogen deuterium, which consists of a proton P and a neutron N. Using Vlasov's theory, a model based on proton tectogenesis conception was developed. The proton tectogenesis conception was begun by Descartes through intuitive insight. He suggested the presence of solar substances in the Earth's depth, and when several centuries later researchers used spectroscopy, they discovered the Sun consisted mainly of hydrogen. Mendeleev assumed that Descartes' deep hydrogen rises upwards within subterranean discontinuities and cracks and reacts with carbon, forming hydrocarbon accumulations, oil and gas. Descartes' insight into solar substances deep underground and Mendeleev's assumption regarding deep hydrogen's role in producing non-organic synthesis of oil and gas led Vernadsky to the next step. He suggested that the heavy and solid Earth's core consists mainly of iron hydride, FeH4. Russell J. Hemley and Ho Kwang Mao from the Carnegie Institution for Science contributed to Vernadsky's suggestion about the chemistry and physics of the Earth's mantle and core. Their discoveries proved Vernadsky's idea and were the first in situ high-pressure, more than 1 gigapascal observation of the reaction between iron and hydrogen. Vernadsky assumed that hydrogen from the Earth's solid core escapes upwards within a liquid core and mantle, asthenosphere and crust, hydrosphere and atmosphere, and escapes into interplanetary space. Satellite measurements during the era of space exploration have shown that fluxes of atomic nuclei of hydrogen atoms move upward from the ionosphere to the magnetosphere. That was called a proton upwelling phenomena, confirming the proof of Earth's degassing model suggested by Vernadsky on the basis of Descartes and Mendeleev's insights. Driven by Descartes, Mendeleev's and Vernadsky's ideas about deep protons moving from Earth's core to outer space, Larin, a geologist and geophysicist, formulated the hypothesis of primordial hydride Earth. The proton tectogenesis, including sporadic genesis of earthquakes, is the main consequence of Larin's hydride hypothesis. In the framework of the non-local statistical model, the migration of the nuclear ions of hydrogen atoms, or simply hydrogen ions H+, is accompanied with deuteron migration through the displacements and discontinuities of strata in the mantle and crust formation. Hydrogen ion H+ is a proton. In other words, the atomic nucleus of light hydrogen protium atom, or hydrogen-1, which is the stable isotope. It has the smallest diameter in comparison with other hydrogen isotopes, such as partial heavyweight, hydrogen-2 or deuterium, the second stable hydrogen isotope, or heavyweight hydrogen-3 or tritium, the non-stable isotope of hydrogen, consisting of 1 proton P and 2 neutrons N. The ratio of proton to deuteron condensate is approximately 10 to the power of 4. The least displacements and discontinuities of strata in the mantle and crust formation, through which protons and deuterons pass, are called hydrogen draw dyes. More narrow displacements and discontinuities in the surroundings of the Earth's interior are called hydrogen-separating subdraw dyes. Fine but frequent protons pass through hydrogen-separating subdraw dyes. Half-heavyweight but rare deuterons are stuck in the bottleneck of subdraw dyes. Migration of isotopes of hydrogen systematically enriches with deuterons the mesoscopic cluster, about 10 nanometers across of mesoscopic scale volume, where 1 nanometers equals 10 to the minus of 9 meters of depth material beneath the hydrogen-separating subdraw dyes. When a pulse of so-called non-local statistical vortex fusion in a mesoscopic portion of deuterons is self-organizing, the deuterons in the mesoscopic cluster under the hydrogen-separating subdraw dyes is said to be in non-local critical concentration, or N and little c. Non-local statistical mechanics operate with non-local statistical distribution functions of objects and cooperation between objects by means of long-range forces of self-action. Vlasov's conception of self-action later became Prigozhin's self-organization and subsequently Harkin's synergetics. In the framework of a non-local statistical model, 3 typical fusion reactions of mesoscopic portions of deuterons in mesoscopic clusters and the energy release are given below. The reaction shows that, due to the acts of fusion of mesoscopic portions of deuterons in mesoscopic clusters, hot isotopes of helium, in other words helium-4 and helium-3, and tritium, hydrogen-3, free hot nucleons, P and N, and hard leptons, gamma quantum, are emitted, some amount of energy is released. Pulses of deuterogenic heat melt mesoscopic clusters, turning them into mesoscopic stoppers.